So, welcome to this third session. Uh, in this particular video, we'll be looking at fixed point iterations. So, fixed point iterations are important and they appear in large number of applications, especially when you have transcendental equations and such kinds of things. So, let us see how it can be done. Okay, one moment. So let us consider the solution of x equals tan h of x, or in fact in general x equal to f of x. So I think someone else should be the host because I have to continuously accept them into the room. I cannot. Hello, are you listening?
Yes, sir.
So you please become the host because I have to accept them into the session continuously.
Yes, sir. Uh,
So actually let us go to matplotlib and plot it. Let me reset everything. Let me make a new script. Okay, so let us first import numpy and import matplotlib. And then let us declare x as linspace going from say -1 to 1 and 100 points. And suppose we want to find the solution of x equals tan h of x. Okay, so let us in fact plot x comma x and x comma tan h x. So the intersection of the two curves will be the solution that we seek. Should be plt dot plot. It should be np dot tan h. Okay, so yeah, the plot does not reveal a lot because near x equal to 0 tan h and x really behave alike. So instead of this, let us use a simpler function. Let us use okay, x square plus 1 upon 2. So what I'm trying to do is essentially if I want to find out the solution of x square minus 2x plus 1 equals to 0. So we all know that the solution for this is x minus 1 whole square equals 0, essentially x equal to 1. So what I want to show through this is fixed point iteration. So let us rearrange this equation. Let us write it as x equals x square plus 1 upon 2. So wherever the curve of x and the curve of x square plus 1 intersect, That is of course the point of solution, and we should be able to see that the intersection happens at x equal to 1. So that is why what I'm trying to do is trying to plot x and trying to plot x square plus 1 upon 2. So let us run this. Okay, so we should increase the range because the intersection we know analytically that happens at x equal to 1. So let us change the range. Let us make it from 0.5 to 1.5 so that we can clearly see the point of intersection. Okay, so at x equal to 1 the two curves intersect, and the intersection of the two curves is indicative of the fact that that is in fact the root where the two curves are equal. Okay, so we know that the root exists at x equal to 1 or in the vicinity of x equal to 1. In general, for a very difficult function, one can only say that the root exists for in the neighborhood of some point. So you can eyeball it and say that look, here is the root. So then you can have a good guess from where you can start. So let me go back to the pad. So how does fixed point iteration work? So I start with a guess. So I make a guess x0. Then I say x1 from this equation. If I call this equation 1, I write x1 equals x0 square plus 1 upon 2. Okay. Then what do? I say x2 is x1 square plus 1 upon 2 and so on. And when do I stop? I should stop when xn and xn plus 1 are not much different. Okay, so they don't change a lot. So what is the mathematical statement of them not changing? It is saying that the error, the relative error, which is 1 minus, so the mod of 1 minus xn upon xn plus 1 or xn plus 1 upon xn, depending on how you define it, this should be less than 10 to the power minus 6 or something. So this is the error threshold. Like in the last class, so this is the error threshold. Okay, so while error larger than error threshold, we have to do x new is f of x old. Okay, where f of x is defined in this case as x square plus 1 upon 2. Okay, then x, so instead of doing x not equal to xn directly, because see, if I do x naught, so I have to again assign x new to x naught, because I want to again do this in a loop. Again I have to do, so essentially what is happening, when I have done x naught square plus 1 upon 2 and assigned it to x1, then I am reevaluating the function with x1. Essentially from this point I could have said x not equal to x1, right? Then I could have again said x new, or in this case x2 would have been x naught square plus 1 upon 2. So I can reassign x new to x naught and again do this in a loop. But the moment I do this, x naught has the value of xn and xn also has the value of xn. So I cannot calculate the relative error like this. Relative error, it cannot be 1 minus x naught upon xn or vice versa. Let us write it xn upon x naught. I cannot do this because xn and x naught both have the value 1. Both are equal. So this simply becomes 0. So instead I have to store x naught somewhere, right? So how do I do that? So I say x old is x naught and then I do this. Okay. So once I do this, I somehow have the value of x old and I also have the value of xn. So I can evaluate this as xn by x old. So once this assignment happens, meaning x old has the value of xn, then this whole loop can go on. X old holds the value of x naught. See, without doing this line, if you try to run the code, if you try to print out the values, you will quickly realize that xn and x naught both have the value of xn, and so you cannot do this anymore. Okay, so you have to keep doing this until the relative error is reached. So let us code it first, and later on we will try to see what actually happens in the program. Okay, so let us go to the program. Okay, so let us keep the two plots. Let us not delete them. Okay, so let us write down the function. In fact, let us define the function def f of x return x square plus 1 upon 2, because I will have many function evaluations and I don't want to keep on writing the whole expression every time. Let us save the file. Okay, I've saved it as untitled. So by mistake I've saved it as untitled. So I will go to files. Okay, I will go to files, save as. I will go to this folder and I will write fixed point iter. Okay, excellent. So yeah, let's see if everything works as expected. Okay, fine, it works. Let us close this. So now we make x guess equal to say 0.7, because from a visual standpoint I know that the plot exists, that the solution for x equals x square plus 1 upon 2 exists near 1, so I can make a educated guess of x guess equals 0.7. So let me call it as x naught. So I have to define, okay, let me do this. So while error is greater than error threshold, I will do, let me write down the naive code. So x new is equal to f of x naught, right? X naught becomes x new, but I have to store the old value, so x old equals x naught. Then I will write error equals np dot abs, so absolute value of 1 minus xn divided by x old. Then I will print x present. I will print out the value of the present iteration, so I will print out xn. So xn, and I will print out rel error, and I will print out error. Okay, let me just put a tab in between. Let me just put a tab in between. In fact, let me print out 6 decimal places. So format xn 3.6f, and relative error, let me print out 8 decimal places. So format 3.8f. So let us see, let us run this. So it says error is not defined. Of course it is not defined, we have not defined anything. So initially to enter the loop we have to define error larger than error threshold. So let error be 1 and error thresh be 1e minus 5. So why have I set error to 1? Because I want that the program enter this loop immediately. So error thresh is 1e minus 5. So while error greater than error thresh, so I just put some value of error which is obviously larger than error thresh to enter the loop. Once it enters the loop, even before the execution of the first iteration, it would have updated the value of error, so I don't need to worry about what the initial value is. Okay, so let's run this. Okay, excellent. So let us look at what has been printed so far. Let us go to the top. So look, at the end of, okay, in fact I have printed the value of x present at the end of the first iteration. Let me just print out for our benefit what the old value of x was. So this is the value of x after the first iteration has occurred, but let us see what the value of x would have been, what the value of x was prior to the finishing of the first iteration. So I will format x old and I will again make it 3.6f. Let me put a tab in between. Let us run this thing. Okay, so now we have the list which contains how the whole thing has converged. So initially x naught was 0.7. At the end of the first iteration, x present becomes 0.745, while the relative error between this and this is this. Then it has used 0.745 as the guess value and updated xp as 0.77513, and it has found out the new error. Then it will use this value as the old value, this new value in the second iteration, it will be used as the old value in the third iteration, and it will update the value of x. So like this it keeps on going. So you see that starting from 0.7 you slowly go towards 1, right? You are going towards 1. If you look at everything, slowly but surely you are sort of converging towards 1, and at a certain point the relative error becomes so small that then you are satisfied, and then the iteration breaks. So while this, the iteration breaks. Okay, so this is called as a fixed point iteration. So let us go back to our pad to see exactly what is going on. So we know that this works logically, algebraically. We have seen that whatever we have done, it seems to work. So let me go back to scratchpad. Let us see what is actually going on by plotting. So we can, even before plotting it on a computer, let us draw the two curves. So so what are we essentially doing? We have two curves, x square plus 1 upon 2 and x. So let me draw. So suppose this is the line x, and so how does x square plus 1 look? Something like this. So this point of intersection happens at x equal to 1. So you started off with a value of x equals 0.7, right? Then what did we do? So x naught was 0.7, then we evaluated x1 as x naught square plus 1 upon 2. So what does this particular line mean? Initially x naught equal to 0.7, yeah. Then x1 is essentially the y coordinate of this function. So the y coordinate of this function is this, right? In fact, let me redraw the curve so that the y coordinate is a bit obvious. I have exaggerated the whole thing to make it a bit obvious. Okay, say something like this. Okay, let it be like this. Rechange the, we'll change the plot again. So x1 is essentially what? It is the y coordinate of the next function. So of this red curve, I need to go to the y coordinate. So this will be the y coordinate. So this is the y coordinate. So this value is essentially, so if this is x naught, then x naught square plus 1 is then the y. So if I call this y, it is the y coordinate of the curve evaluated at x naught. So this becomes x naught square plus 1 upon 2. Then what happens? I assign x0 to x1. So what is this assignment meaning? It means that, okay, instead of doing it in a programming way, let me say x2 then becomes x1. So let me call it this. So what is the meaning of this assignment? The meaning of this assignment is this x1 that we have obtained becomes x2. So I map it to y equal to x plot. So this particular value becomes x2. This value over here becomes x2. Because this line, the equation of this line is y equal to x, and this particular point is x1. So all the points on this line are y equal to x. So if what will be this point? The coordinate of this point will be x2 comma x2, but we already know that the y coordinate of this point is x1. So this x2 is actually x1 because this equation of line is y equal to x. Okay. So therefore we have taken this y coordinate and mapped it on to the x axis. So this becomes x2. So now x2 is x1. So let me rub this. So let me just readjust the curve. But I think it is not required. We don't need to readjust the curve. Now we will do x3 is equal to x2 square plus 1 upon 2. Then we will again go to the function evaluation. If then it will be again mapped onto the y-axis. Then it will be again mapped onto the y equal to x line. Then it will go like this. Then it will be again mapped onto the x-axis, to the function. Then it will again go on the y-axis. It will again go on y equal to x. Then it will again map onto the x-axis. Then it will be again mapped to the function like this. Then it will again go to the y equal to x line, again come back. Like this, we see that the guesses are converging towards x equal to 1. I think it will be even clearer if we try to plot everything. So what are we essentially doing? So whatever the initial x0 was, the very first point that we have, so the very first point that we have will be x0 comma x0. Then we know it goes on to, okay, this will diverge. Let me rub this. So the first point will be over here, then it will go on to the function, then it has to go to the y-axis. So over one iteration, we need to plot 3 points, x0 comma x0, because this line equation is y equal to x. Then we will plot x0 comma f of x0, right? Then we will plot f of x0 comma f of x0, because this y, which is f of x0, is mapped onto the line y equal to x. So if y is mapped onto the line y equal to x, automatically it will become f of x0. Alternately, because we are assigning f of x0 to x new, so this point will be x new comma x. So then per iteration, this will happen like this, like this, like this, and it will converge to the solution. So this kind of convergence to the solution, that kind of plot is called as a cobweb. So cobweb is something which Spyder makes. So a spider pattern, this, I mean, this resembles sort of a spider pattern, right? Not spider pattern, but a spider web pattern. So that is called as a cobweb. And such kinds of things also occur in analysis of microeconomical models. So if you have ever come across certain microeconomics models of supply, demand, and all those things, such kinds of plots are also seen where demand and supply, how they are changing is seen. Okay. So let me go back to the program so that we can add the plot. So before doing that, let us change the range of the plot from 0.69 to 1. Let me just quickly plot this. Okay, so whoever is trying to annotate the plot, please don't do it. Okay. Anyway, so let us start. So before plotting, for plotting of the lines, we need to define an array of 3 points. So we will define x plot equal to np dot nd array 3, and we will also define y plot as np dot nd array 3. This means that we have created an array, we have initialized an array of 3 points. So here we will define it as x plot, not here, x plot 0 is equal to x naught, and y plot 0 is going to be also x naught. So this is the first point that we had defined. Then what will be the second point? The second point will be x plot 0 is equal to x naught, and y plot, this will be 1 because the 0th point has already been defined. Y plot 1 will be f of x naught, and after evaluating xn, x plot 2 will be what? It will be xn, and y plot 2 will be equal to also xn. So like this we can visualize the plot. So after having all the points, let me just do plt dot plot x plot y plot, and let me make it a black line. Okay, so let's see, let's run this. Okay, so there you see. So we've started at this point, then we've gone to the function, we've mapped the function to the x equal to y line, then again we've gone to the function, we mapped it onto the x equal to y line, again did this, and so on. And so after how many iterations does it converge? So suppose someone asks me, after how many iterations has the whole thing converged? So we don't know that. So let me define a simple counter. I will say count equal to 1, and at the end of each loop I will say count equal to count plus 1. Then I will write here iter count, I will put a tab. Okay, so I just printed out the number of iterations. So let us print it out. So it has taken 440 iterations to converge to the solution. So if I sort of increase the threshold in error, yeah, whoever is doing this annotation, please don't do that. If I reduce the number of iterations, so I converge very quickly, I converge with only 40 points. If I reduce this further, suppose I make it like this. So look, I'm actually converged to this solution, but because the threshold in error is so low, rather it is so high, then I have converged to a reasonable amount of confidence. Okay, so this is how fixed point iterations are done. Okay, so I'll close the session. So in this session we have seen how to do a fixed point iteration. In fact, let me just conclude by saying that not just transcendental equations, but it can be done for various kinds of equations also. So suppose you have equations of the form, suppose you want to find out the root of sin x. Okay, suppose you want to find the root of this, so you just say x plus sine of x equals x. I just add x on both sides, so then this thing becomes fx and this is x. So essentially we have reduced it to the form x equal to fx. So then I have x1 equal to x naught plus sine of x naught and so on, and I keep on doing the iteration. So I can cast any nonlinear function also in this particular fixed point iteration form. However, fixed point iterations do not always converge. They do not always converge. The guess value, so I leave it as a homework to you. If the curve is something like this, and if you make guess value of over here, right, so this will get mapped to the function then on the xy axis. So if it is like this, then it keeps on diverging. Instead of going to the solution, it keeps on diverging. But if you make the guess value over here, so it will converge. So the slope of the curve f of x has to be less than 1 in the zone of guess. If the slope is not less than 1, then this convergence is not guaranteed. Let us see whether that is true. We can go to our plot again. In our plot, let me take a guess on the other side of 1, because once we cross 1, the slope of the curve increases. Let me just plot everything just to show you the curve. Let me clear this. So let me take the guess value, instead of 0.1, let me take it as 1.1. So look, it's stuck in a loop. Okay, initially it was over here and then something has happened. Okay, let me increase the tolerance. Because I know it will diverge, let me put a limiter on the iteration. So maximum number of iterations, say we allow is 200. And count is less than iter max. Actually this AND is a bitwise operator, so this should be AND. So the result is too large, it means that it has diverged. So let me say iter max is 20. So look, it started here and it is quickly diverging. Instead of converging to x equal to 1, it is diverging. And the reason is, in the guess value zone, the slope of the curve is larger than 1. And if the slope of the curve is larger than 1, then instead of converging, the fixed value iteration always diverges. So this is something which you need to be careful about. Okay, so I hope you've learned something. I hope at least you have learned how to make a plot more detailed, because if you look at any book, rather than showing just how iterations converge, you want to actually explain the phenomenon to someone. So you need to make a good plot. You need to make a good case for yourself. Okay, so with this we close this session.